Alright, so now we are ready to talk about the first law of thermodynamics. Okay, we already know the zeroth law. The zeroth law simply tells us that, hey, system A in equilibrium with B and system B in equilibrium with C implies that system A is in equilibrium with C. Okay, which allows us to talk about thermometers and all those things. Anyway, the first law of thermodynamics is says the following: if you have a system and let's say that you add some heat to the system Q and you also do some work on the system, then essentially what it says is that as a result of these two external things, okay, you are going to change the internal energy of the system. So what it says is Q plus W is equal to delta U. Alright, so it is essentially the energy conservation law. Okay, so if you're adding heat, if you're doing work, you're going to change the internal energy of the system. That's it. It is as simple as that. It's a very simple law, and we'll see that although it's a simple law, there are lots of things you can do with it. However, it does not tell you what kind of processes are restricted. Okay, and we'll talk about that a little bit when we discuss the second law of thermodynamics. The second law of thermodynamics tells you what processes are restricted. For instance, okay, if I have a hot object in contact with a cold object, okay, if I have something hot, okay, so let's say I have hot and cold, okay, we know that when they are in contact with each other, they're going to exchange heat with each other. Okay, heat will be exchanged until we reach thermal equilibrium, at which point the temperature is going to be fixed. Okay, now in this process, clearly the hot we know loses energy, the cold we know gains energy. So this guy loses, okay, and the cold gains, okay, in such a way that the net change, net delta Q, okay, is equal to 0 for the system. Alright, so clearly energy is conserved. Now on the other hand, what if we had a process which basically went in the opposite direction, where the cold was to lose and the hot was to gain an equal amount of this energy? Alright, now the first law does not put any restrictions on it. It says that, hey, it's possible, because the hot could get hotter, the cold could get colder, but in such a way that the net energy is always remaining fixed. Alright, however, we know from experience that that never happens. Okay, because if it did, it would take care of all our energy crisis issues. Okay, so that does not happen, and the restriction is imposed by the second law of thermodynamics. So we'll talk about that a little later, but in the meantime, here this simple law will be enough for stuff, for whatever we need. So let's do an example. Let's see how to apply this law. Alright, let's go to a process, the process that we've already looked at, and let us say that we take our gas from volume P0 V0, okay, to a new thing which is 3P0 and 3V0. Let's take it from process A to process B, and we'll ask in this process what is going, how much is how much heat has been absorbed by the system. So let's say we have n moles of a gas, okay, and we want to find out our goal is to find the total heat that is absorbed or released in this thermodynamic process. What is going on? Alright, so we're going to use our first law of thermodynamics, which says that Q plus W equals delta U. Okay, and so Q will be equal to delta U minus W. So to find the heat, we'll have to find the change in the internal energy and also the work done. Now, in previous problems, we've already done this. We've already found the amount of work done for the cycle. Okay, the work done on the gas. Now, if you recall, if you just go back and go back to, I think, the video on work, okay, under the thermodynamics section of videos, you'll see the work done. And to find the work done, all we have to do is find the area, okay, enclosed by the curve and the x-axis. So this is essentially, this area gives us the work done, and if you do it correctly, okay, we get the work done to be negative, and the negative is because the gas is expanding. It will be negative 4 P0 V0. So this is the amount of work that is done by the gas. Now, on the other hand, let us find the internal energy change, and which was something we did in the previous video, and the change in the internal energy for the process A to B happened to be 12 P0 V0. Okay, so now that we know these two things, okay, and if you're unsure about this, just hit calculate it, make sure that you verify. And to find the internal energy, you'll have to find the temperatures at A and B, and then use 3/2 nR delta T. Okay, I'm telling you that this is all a monatomic ideal gas. So Q now happens to be equal to delta U, which is 12 P0 V0 minus negative 4 P0 V0. Right, and this will end up being equal to 16 P0 V0. So this is the amount of heat. Okay, now since the sign is positive, we know that this is the heat that is absorbed by the gas during this process. So if Q is positive, heat is absorbed by the system. Okay, on the other hand, if Q is negative, we know that heat is released by the system. Alright, so this is the answer to this question. Let's look at another situation here. Alright, now let us look at a cycle. Alright, now let us look at the cycle that we have already talked about. So once again, we go from PO, what am I doing? PO, VO, and we go to say 3VO and 3PO. Okay, so this is A to B, then we go to C, okay, and then we go back to A. Now, for this cycle, we ask the question, what is Q for the entire cycle, A to B to C? Okay. Now, the answer for this is actually very easy. And if you recall, okay, once again, our law of thermodynamics says the following: Q for the cycle plus work done for the cycle is equal to change in internal energy for the cycle. Okay. Now if you recall from the internal energy change video, would we already know what delta U is? For any closed cycle, for any cycle, delta U is equal to 0 because we bring the gas back to its original temperature, original state, which means that Q for the cycle is simply equal to negative of the work done during the cycle. Alright. Now in this case, for this cycle, we also know how to find the work done. Okay, and that's very easy. Just find the area enclosed by the cycle. In the first video on work, we talk about that a little bit and why it is the area under the cycle. Okay, so let's find the area under the cycle. And this is simply equal to, so it will be negative. Hold on, I'm going to make this change here. So it will be, first it is negative, and then we need to find the work done by the cycle. And since this is a clockwise cycle, the work is negative by the cycle, so it is minus, and then there's a negative sign, and that is half of the area by the cycle. So the base is 2V0, the height is 2P0, and so the net work is going to be equal to 2PO. Okay, and or rather the Q for the cycle is going to be equal to 2PO. So again, in this cycle, in a clockwise cycle, heat is absorbed. Okay, there's a net absorption of heat. Now if you recall in the previous problem, we saw that for the process A to B, okay, during the process A to B, the amount of heat absorbed, okay, let me get rid of the red signs here. For the process A to B, okay, heat was absorbed, and the amount of heat that was absorbed, okay, was equal to, we know, as what was it? We had 16 POVO. So 16 POVO was absorbed. Okay. However, for the entire cycle, we see that the heat absorbed is only 2 POVO. That means a certain amount of heat was also released. So that actually happened during during these parts. Okay, so some amount of heat was released here and some amount of heat was released here. Okay, so we can actually calculate the amount of heat released during the process B to C and C to A. We will make that one of the upcoming videos where we'll calculate all the stuff for each part of the cycle. Okay, but we know that this amount of heat was released during the cycle. Okay, so to calculate the work done in a cycle, or rather to calculate the heat absorbed or released in a cycle, all you need to do is find the work done. Okay, because the internal energy for a cycle remains, the net change of internal energy is 0 for a cycle. As a result, Q for the cycle is simply equal to negative of the work done during the cycle. And if it's a clockwise cycle, okay, then the work done is going to be negative, as a result of which Q will be, there will be a net absorption of heat during the cycle. And on the other hand, in a counterclockwise cycle, there will be a net release of heat during the cycle. Okay, so this now we have all our components. We know the work done, we know the internal energy change, and we also know how to find the Q for the cycle. Okay, so in the next videos we'll look at we'll look at engines, and we'll discuss more things about cycles, and we'll learn about how to find efficiency for an engine and all kinds of things. All right, so that's it for this one.